This week we're going to start doing something in addition to what we do in a Practiclass. We're going to add about 15 minutes, and that's going to give us a chance to do a little 10-minute, what I'm calling lecture vignettes. Little things from cognitive science and neuroscience that inform us how to learn. Helps us understand what's going on in the brain and what's going on with our psychology as we learn things. You know, one of the most important things in learning is something I call you gotta give them the why. Why am I doing things? Because folks, teachers out there, the jig is up. Kids know we're 1,000 years old and we never were their age. We can't possibly understand what it's like to be them because we never were a child, and they'll come up with a better way. Now, it's interesting, if it were something like weightlifting, no one thinks twice about how that works. We know that if we go in, it would be hard, we lift weights, our muscles get bigger. We know this because we see other people get that way, and they tell us how they did it. I did this through weightlifting. When it comes to cognitive skills, or skills that express themselves, say, through our fingers don't get bigger when we play scales, right? We can only assess by how much skill we've acquired, like how much better we've gotten. And since we don't know the process that's going on in the brain, it's almost like as if we lifted weights and then we gauged the skill. Look, I can lift much heavier things easier. I have talent. But that's not what's going on. Only because it happens in the locked box of the brain do we say those sorts of things. So when we start learning how that works, we end up with a choice just like weightlifting. If if I want to get my muscles bigger, I do this. If I do anything else, it won't do that. I don't have to do it, but I don't wonder about the results either way. When it comes to learning music, we're making up stuff all the time because we think there's some magical thing called talent that's brought in by a unicorn ridden by a nymph sprinkling talent dust on us. There's no evidence for talent, by the way. There's none. There's only anecdotal stories, but that's a lecture for another day, and it will be. So what we're going to do is we're going to delve into the neuroplasticity of learning, how the brain changes and how we change the brain over time. And how it learns. Knowing this will help us make decisions as to how we work. Of course, these lectures are very incomplete. There's no way even we're going to talk about the small area of the neuroplasticity of learning in 10 minutes and do it in any sort of comprehensive way. This even goes for my 90-minute lectures that I give around the country. We're never going to get to everything there. But not having everything is certainly not a reason not to have very useful things and small things as long as we understand what they are. So if I can start screen sharing here, what we're talking about is neuroplasticity. Sorry, I just lost something here. There it is. How the brain changes based on our thoughts and actions. In fact, all our thoughts and actions do change our brain. Your brains are changing right now as I speak to you, hopefully in a good way. And we are in control of these changes, not the universe, not something else. And how well we play and how well we learn to do music is a result of how well we manage these changes. In neuroscience, this is called neuroplasticity, and it's an idea that's only really been on the table since the mid-2000s. For many, many, many years, researchers believed that the brain stopped developing around the age of 18, and no significant developments happened afterward. We now know not only is that development under our control until 18, but it's under our control and continues our entire lives. You can learn new skills. Listen, all prodigies have is that they started way earlier. They had plenty of time to do it. They didn't have kids. They didn't have to go to a job. And they didn't have bad habits to break, along with having good teachers with them. But they're no different than we are. The real thing about prodigies is that they're able to engage the prefrontal cortex of the brain, which forces us to do things we don't want to do, and force themselves to do the type of work over time. That's the real thing that's at work in prodigies, and that's just developing another part of the brain. So through thought and action, we change our brains to function as we wish. And before we start that, I want to talk about something that's prevalent enough that people have written about it, and that is the idea that we hear about some study on the news, and it says if you keep your right arm above your ear level for at least 10 minutes a day, it will make your violin playing better. One study is just one study. It's valuable if we've been doing something for years and it works, and then we hear about a study that verifies that. That's helpful. It doesn't mean it's true. But just going and doing something because someone had a study, and then we get discouraged because it doesn't work or we didn't follow directions, that's not the way to do things. There's a lot of stuff out there that is really deceptive. We don't know a whole lot about the brain. We're just being able to see into it just a little bit. What we do know is really instructive. But these videos going around showing the brain all lit up, and by the way, the brain lighting up is just added to the image of fMRI images. It's just where the blood is going in the brain, which is where the action is happening, we think. But this idea that playing music is a full body workout in the brain, that's a marketing tool to help someone get gigs and sell things to you. For instance, we've heard of the Mozart effect, right? If you listen to Mozart before a math test, you'll get better grades because you have better spatial reasoning and all this stuff. Turns out that that was a flawed study. That was out in the 90s. It's been debunked. But yet, type in baby Mozart and go see how many people are using this to sell a product. So we have to be really careful. It's in others' interest to deceive us about these things sometimes, and we sometimes don't make the best decisions on small bits of information. Researchers have noticed this, and they have come to call it Neuromyth. And this is from a paper written by someone named Mariel Hardiman, who's a researcher. The popularization of neuroscientific ideas about learning, sometimes legitimate, sometimes merely commercial or political, poses a real challenge for classroom teachers who want to understand how children learn. So let's be really careful and suspicious of everything everyone says, especially if they're not well versed in the field, especially about neuroscience. So here's what I'd like to tell you about neuroscience. Let's start with the idea of neuromyth. When I'm at my site visits, when I do my lectures at different colleges and high schools, I talk about this, and I say, so how much of our brains do we use? And no one answers because they know where this is about to go. Right? Do we really only use 10% of our brains? Researchers have looked to try and figure out where this rumor started, and nobody knows. Who knows where it came from? What I think it is that it represents that we really only use 10% of our effort. So that is essentially not using enough of our brain. But what's the real truth? Here's an image, 3 images of the same brain in an fMRI, functional magnetic resonance imaging. Here's 3 images, 20 minutes apart, of the brain learning a task that can be learned within an hour. So we have 20, 40, and 60. It was a cursor tracking task, and for our purposes, it was a motor skill. Notice first, the brain is very active. It's a lot more than 10%. We must be doing something right, because look, we have a lot more than 10% going. And looky here, this is the prefrontal cortex we spoke about a little bit earlier, the part of your brain that makes you do stuff you don't want to do. Look how active it is. You notice how frustrating it is when you're first learning something, or you're trying to get it down, you don't know what to do? That's what's going on here. It's forcing your brain to try all this stuff out and try to figure it out. Boy, it sure looks like we don't have talent in this stage. A little bit later, and granted, it's not always 20 minutes, this particular task was, so you can't rely on the time frame here, but this is the process that happens. It happens more quickly much of the time, sometimes longer. Now what's happening? The prefrontal cortex starts dropping out, less areas of the brain are needed to make sense of it, and finally when we're skilled and we have the skill learned, no prefrontal cortex, you know, when things feel automatic and easy to do, and the brain has figured out the exact small portions that are needed to get the skill done. That's called a process efficiency change. That's right, it's better that we use less of our brains than more. So let's get that one out of the way. What's going on? We're building neural networks here. Neural networks are neurons communicating with other neurons. So once the brain figures out, hey, all these neurons need to communicate, here they are, here they are, here they are, and now they are neural networks wired together. When I do this, that's a group of neurons, a neural network, firing off to make me do it. When I do this again, it's the same thing. So let's discover what a neural network consists of. It consists of neurons communicating with other neurons. You don't need to know the technical terms, but I'll use them just to be correct. The way they do this is an electrochemical impulse called an action potential originates in the neuron. It is then sent down an axon, out over a gap called a synapse, and then into a dendrite, which is a receiving branch of another neuron. And this is going on super fast all over your brain all the time for everything you do and think. All your cognition is represented this way as well. Now, when you first build this, there's no insulation on the axon, and the signal leaks out. So it doesn't really get to where it's going as fast as it needs to get there, and certainly not with the strength. If you look outside at the power lines, you notice they're all insulated, right? Why is that? To keep the power in there and moving fast and strong to its destination. Is there anything represented by neural networks that you would like to be faster and stronger? Right? So we built this network, we've learned a new skill, now we want to get it faster. What's the deal? Well, every time we send an action potential down an axon, it triggers a cell called an oligodendrocyte, to produce a lipid protein called myelin. Myelin's an insulator. And so it starts wrapping and wrapping, insulating the axon over and over again until the signal gets stronger and stronger. This is why repetition works, especially in the early stages, to strengthen. Now, you've heard your teacher say many times, don't practice mistakes, you'll play mistakes. That's true. It doesn't really land with us, does it? Well, how about this? You're either triggering oligodendrocytes to produce myelin on the neural network you want, or you're triggering it on a neural network you don't want, which is the mistake. Now, if you have play something 5 different ways and make all kinds of mistakes for the weeks leading up to your performance, is it any wonder the night of the performance you have 5 networks ready to go? Which one are you going to choose? You got a 20% chance, 1 in 5, of getting it right. And by the way, you're going to be nervous. You're going to have your working memory overloaded with these thoughts. It's going to be hard. So yes, proper repetitions slowly are what helps the brain myelinate axons for stronger performance. So it's your choice. Do it one way and get it right, or do it the other way and don't. Going back, and here is a picture of an axon with myelin wraps around it. I love this picture. It's an electron microscope picture, and it just shows how this insulates the axon. It's the only picture I'm aware of this. You can have up to 400 wraps of myelin, and you certainly don't get 1 wrap every time you do a repetition. So, slow, accurate repetitions, slow, accurate concentration in the learning phase to build the proper neural network, and know that you are in control of your brain and how it builds and changes. Because every time we learn something, every time we take in anything, we change our brain either functionally or physically. Functionally, different parts that didn't communicate before now communicate for the new skill. Physically, parts of our brain take over other parts of our brain. Representations, neural representations, take over more of the cortex. For instance, in violins, they've done scans where they find the left-hand representation in the cortex takes up much more area than people who do not play violin. And the reason is because violinists practice this stuff over and over, and little by little the brain changed to give more area to that because it was obviously a skill they were focusing on and paying attention. So, use your brain well.